So the topic of my talk is key phrase indexing with controlled vocabularies. And this is what I'm doing my PhD in, which is funded by Google. I studied at the University of Waikato in New Zealand, and this is where Craig Neville Manning did his PhD, and we have the same supervisor. And the system that I'm going to describe you today is the successor of the system that Craig has been working on, called key phrase extraction algorithm. Indexing means assigning terms to documents so that they describe these documents' main topics. I would like to show you an experiment we have conducted with the Food and Agriculture Organization of the United Nations. They have a very large document repository and professional indexer who index documents by using terms from a domain-specific thesaurus called AgriVoc. And in our experiment, we had 10 documents all related to the agricultural domain, and 6 professional indexers from the FAO have assigned terms from the AgriVoc to these documents. The AgriVoc has 17,000 descriptors, the version that we have used, which are terms that the indexer are allowed to assign, and there are 11,000 non-descriptors, terms that are linked to descriptors, which helps the indexers to keep the indexing consistent over the document collection. For example, if there is a term obesity that appears frequently in the document, the indexer is encouraged to use the term overweight instead, so that documents on overweight and obesity are grouped under the same location. Here's a typical entry from the AgriVoc thesaurus. The descriptor epidermis is followed by a short scope note describing its usage, and there are a few related terms, semantically related descriptors, broader and narrow terms, and you can see that they're aligned in a kind of hierarchy. The thesaurus has a hierarchical structure, and for some descriptors have related terms which represent general relatedness without specifying what kind of relation. So here is a sample document, an example document on the global obesity problem. In my first 2 days at Google, I experienced your healthy lunches, and I know that you don't have this problem. Our 6 indexers have assigned 33 terms from the AgriVoc to this document, each of them between 5 and 11 terms. And all of the 6 indexers have agreed only on one term, overweight. These 4 terms are terms that at least 3 indexers, half of them, has agreed on. These are 12 terms that at least 2 indexers have selected, and the majority of the terms were selected by just one indexer. They were idiosyncratic to each of the indexers. To compare it, 2 of the indexers, I marked the choices of one of them with blue and the second one with red circles. As you can see, the only term that they agreed on is overweight. Indexer 1 selected dietary guidelines, diet, food, nutrition policies, price policies. Indexer 2 was a bit more prolific and selected more terms. Generally, when we evaluate automatic indexing system, we compare phrases that were extracted automatically to the ones that were assigned manually. So if we would imagine that the second indexer would be an automatic algorithm and evaluate the system, it would be a complete disaster for the system, because only one term would be identified as correct. In this case, all terms are correct. And you can see here the semantic relations between the terms as they exist in the AgriVoc. And actually, the terms are not that different. They all relate to the domain of the agriculture. On this slide, I have shown you the choices of all 6 indexers. It was very interesting to look at such diagrams, because here we can see effects that are not obvious when we just see the words separately. It is quite obvious that terms that were selected by most indexers, overweight, nutrition policies, price policies, are terms that are more important for this document. Also, some terms are related to more other terms. For example, nutrition requirements is related to 4 terms, developed countries to just 1 term, and public health or regulation are not related to any terms. The more terms a phrase is related to, the more significant is its meaning for this document. So if we would evaluate the quality of the indexers, the one who performed the best would be the one who selected terms that were assigned by most other indexers, or terms that are related to most other indexers. And this is, yes?
Could you give us a little bit context, because I'm not very familiar with this, why, who are the potential audience for this index terms? For librarian, or for readers, or for just general web users? Why do you pick the index terms?
Your question is, what is...
who are going to use
who needs the indexing? Well, index terms are important to access document collections of any sort on the internet, in libraries. When you see published papers, they're always somewhere underneath, in the first part before introduction and abstract, keywords. This is the same thing for phrases that authors have assigned. And when key phrases are selected from a controlled vocabulary, as I've shown you with this example with overweight and obesity, it helps to access the document quickly, and they're all grouped together under the same topics. Also, if you would have search results and each of the document would follow by a set of index terms that describe its topic, it would be easy for the user to see what they are about. And in libraries, digital libraries especially, they're of even greater importance. The library subject heading is a standard way of classifying library entries, and I hope this is the answer to your question. Okay. So how do librarians evaluate indexing? They use the term called inter-indexer consistency, and it is measured with some formulas that remind you, and some familiar one from the area of information retrieval. Basically what they do, they compare the number of terms 2 indexers have in common to the number of terms each of them assigned to the same document. There were a few studies on indexing consistency, and they all had in common that indexers seldom agree on terms that describe documents' topic. They rather agree on concepts. Yes?
So what happens if A equals B? Then M1 will be 2 and M2 will be undefined. So what would this measure? What is measured? If the value is 2, so suppose that they all agree. Is it? I mean, the question is, what is the meaning of those values? M1 could range between 0 and 2. Oh, sorry, between 0 and 1. Sorry. I'm retracting this.
Actually, when I analyzed these formula, I discovered that the M2 is actually always lower than M1, and M1 is very similar to the F measure. I'm not sure what is your question.
No, I was confused.
Okay. these are the standard formula that librarians have been used, and some of them computed the number of matching terms by taking into account semantic relatedness between terms, and in that case consistency was higher. However, there was no standard way of computing consistency by taking into account semantic relatedness. In our data, we had also noticed that indexers rather agree on concept than in terms, and in a new measure that we have been working on, we tried to include the semantic relations into mathematically way that makes sense. For a new measure in inter-indexer consistency, we decided to adapt the vector model and to represent the set of index terms assigned by a single indexer as a vector with number of elements in this vector corresponding to the size of the controlled vocabulary, and either 0 or 1 if the terms was selected by the indexer or not. Then consistency between two indexers is the cosine of the angle between two vectors representing two indexers' index term sets. And the measure is the standard cosine correlation measure. Now, how do we include semantic relations? We can represent relations that are encoded in our controlled vocabulary with two matrices. One matrix represents the symmetrical relations RT, which are general relatedness, and the generality matrix represent asymmetrical relations, broader and narrow terms. For each of the relations, we want to measure its significance. Exact match, how important is it when terms match exactly, when they're generally related, or when they're in hierarchical relations to each other? And to keep the measure balanced, the sum of these weights should be 1. The matrix and the weights are included into the new measure in this way. And this is the formula that represents the overall consistency over all indexer and all documents in our example collection. Because we're dealing with professional indexers, we think that they actually can be seen as gold standard, and we can choose the weights for exact relations, general relatedness, and hierarchical relations to maximize the result of this measure. And we did that, and the results were 0.2 for general relatedness and 0.15 for hierarchical relations. Our indexer have achieved 38% with the first standard measure used in the libraries. The vector model without semantic relations gained 49%, and when we included semantic relations in this way, the measure improved by 2%. We were, yes?
Sorry, where the R and T come from, the relationship between the terms?
From the agravoxysaurus.
So you already have, it's predefined or something?
The relations were predefined by professionals who created those thesaurus. Yes?
Sorry, am I reading that right? You say that only about half, if you have professional index experience, only about half of their terms and things are
Only about half?
I'm looking at those measures, and they're 40–50%.
Yes.
So if two professional indexers, they go in the index document, and they each put 4 terms on it, you only have 2 of them at all.
The question is how this number was computed, right? Do you understand correctly?
The question is, I expect
So
it to be more consistent than
in this measure, 38%, we did. It is computed with the measure I showed you on this slide. So if indexer agreed on 2 terms, it's 4 here, and depending on the number of the terms in total, it's divided.
So in other words, professionals are not very good.
Yes. Okay. I was trying to make my slides more pretty, and I found this picture, and my supervisor told me I should better remove it. It's a kind of sexist picture of an older lady who is not very pretty, our stereotype of a librarian. I didn't remove it because it's actually not a woman, it's Benjamin Franklin. And I discovered that he was a librarian as well, and he actually founded the first lending library in the United States. Obviously, professional indexing is expensive and time-consuming, and I hope I could show you that the consistency is low, under 50%. Even for professionals who do this job every day and that they know that we actually measure their consistency. Even if the same person does the job on different days, it is not consistent with itself, with himself. However, consistency is important. There have been studies that confirm that the higher is consistency in a document collection, the higher is the retrieval efficiency. So why do we employ humans, although their performance is so bad? Because keyphrases are such a valuable resource. I mentioned earlier that they are very useful to organize documents, to provide quick access to them, and they can be used for all the different sources to improve interaction of the user with the document collection. And of course, there are different ways. There have been a few approaches to do this task automatically. I have classified the existing approaches for automatic indexing into 2 groups. The keyphrase extraction approaches are quite straightforward. The document is analyzed, and n-grams or noun phrases are selected that appear in this document. Then the characteristics of these candidate phrases are analyzed, and the most significant of them are selected into the set of key phrases. These approaches are easy and fast to implement, and they do not require much training data if these are machine learning approaches. However, they are mostly restricted to syntactical properties of phrases and do not take into account the meaning of phrases. The quality of extracted phrases is often low because of some mistakes in n-gram selection or noun phrase extraction approaches. And most importantly, keyphrase extraction approaches are not using control terms. So once they are extracted, there is no consistency over document collection, and which is quite bad. The keyphrase assignment approaches, also known text classification, text categorization approaches, is where documents are clustered into groups according to words that appear in this document. This cluster may overlap, and once a new document needs to be classified, it is compared to the clusters and assigned to the most similar ones. If we assign the label to each of the class, we have the same result, a document with automatically assigned key phrases. These approaches are more accurate because they do take into account the meaning of words. However, they need large training corpus. We need to create a cluster for for each key phrase, basically. And if we have a very large controlled vocabulary with 17,000, for example, like in the case of AgriVoc, or library of subject heading has about 1 million of terms, these approaches are not practical. Craig has been working on key phrase extraction algorithm that can be classified into this group of approaches. And when I came to Waikato, I tried to improve it, and I decided to combine it with the controlled vocabulary, and I called the system Kia++. I don't know if any of you have ever been to New Zealand. Kia is actually a native parrot bird of New Zealand. And these are birds that make traveling in New Zealand dangerous. They're especially common on the South Island, and when tourists rent a car and leave it in the parking space and go and visit some fjord or go for a walk, they might come back and discover their car destroyed. They like to pick on these rubber parts. They pick up stones and throw them on the heads of the tourists and steal their food. They're very clever birds, and I think it's a good name for an algorithm. Now, how does it work? We have a set of documents, and in the first stage, as I noted before, we need to extract candidates. Previously, we did not have a controlled vocabulary. In this case, each engram that is extracted, I map onto controlled vocabulary, I check, is it actually a valid term? To ensure better matching, I'm using a pseudo-phrase technique, where in a phrase, all stop words are removed. The remaining words are stamped and ordered in the alphabetical order, so that phrases like predatory birds, predative birds, bird predation are all mapped onto the same phrase. Also, which is not shown in this diagram, if I identify a non-descriptor in one of these terms, I include the corresponding descriptor instead. So the candidate set may contain phrases that actually do not appear in the document. In the next step, I need to identify which of the candidates are the most significant one, and to do this, I compute their characteristics, so-called features. This is one of the important steps, and I'll tell you on the next slide what features I've been using. Kia++ is a machine learning approach, so we need to train it. To do this, we use a document collection with manually assigned key phrases. And for each of the candidates, we can then see, does it appear, was it selected by the humans, is it a positive or negative example? And depending on how the feature values distributed among the positive and negative example, we compute our model with naive Bayes. This model is then used to compute probabilities for phrases for candidates where it is unknown which are the significant ones. The one with the highest probabilities are selected into the final key phrase set. The first two features that I've been using are the same as in the previous version, TF, IDF, and the first occurrence. The latter mean that if a phrase tends to occur in the beginning or in the end of the document, it is more significant. I added two new features. When I compared the distribution of phrase length in the controlled vocabularies and among the phrases that were selected manually, I discovered that the distribution differs. Professional indexers tend to select longer phrases. So I use this feature, and no degree is kind of semantically enhanced feature. When you remember the diagram with overweight, obesity, and other terms that are shown how they're related to each other and how indexer have selected them. We have said that the ones that are related to most other terms are more significant. The same in the documents. If a phrase is related to most other phrases in the document, then it is more significant for this document's content. Here is a sample document on bird predation. Terms that are valid index phrases are marked, and here are they in the same diagram form with semantic relations between them represented as black lines. Here's the term bird predation, was mapped onto predatory birds. Predation occurs here and birth occurs here. So the no degree of this term is equal to, and in this example, this is a potential key phrase. I use three different ways to evaluate K++. The first is the standard way of evaluating indexing approaches, where we compare it to phrases that were assigned manually. We use tenfold cross-validation and have computed precision, recall, and F-measure, and compared how the values differ from the previous version, care, and the results were twice as better as care's results. When I tried to take into account semantic relatedness in the same evaluation, I counted as a hit or correct phrase cases where phrases do not match exactly, but they are related. And care plus F measure was 50%, and the difference to care was even higher. Indexing consistency, in my opinion, is a better way to evaluate automatic systems. Our goal to have an automatic system which is at least as good as human indexer, and that could be the 7th indexer in our experiment. So ideally, the algorithm should achieve as high consistency with humans as they among each other. I've shown you that our humans have achieved 38% with standard measure and 51% with semantically enhanced vector model measure. Unfortunately, K++ is not as consistent with humans as they among each other. It has 11% less with one measure and 13% with the second measure. So there are definitely room for improvement. Yes?
You have like 4 features. You can have any idea which one is more important?
Yes, I've done that. When I was experimenting with features to include, I evaluated the importance of the features, and no degree did contribute much more to the results, whereas phrase length, just a few percentages, but I still left it in the algorithm.
Only 10 documents when you compare it to humans. The sample is too small.
Yes, this is correct. The sample is very small, and we need data to evaluate it on larger collection, but it's just so difficult to acquire. It is very hard to convince librarians or other people to index the same documents over and over again. We're working at the moment on ideas how to overcome this problem. For example, we're thinking about using students in a class on digital libraries and give them computer science articles so they can index them so we can have a larger set. If you have any connections to libraries, let me know. Yes? Just behind was earlier, sorry.
So if I understand right, the index phrases, the key phrases your technique gives are always phrases that appear in the document.
can't hear you so bad. Could you please speak louder?
Is it true the key phrases you get, they're always phrases in the document?
No, it's not true because I mentioned we do this non-descriptor to descriptor mapping.
Okay.
So if a phrase does not occur in the document but is semantically related or equivalent to a phrase that occurs in the document, we replace it by that phrase. But
you have some list of mappings from phrases that might appear in documents to phrases that you use instead of the phrase.
yes, where I mapped phrases, noun n-grams to the controlled vocabulary to extract valid phrases.
And that was one of the things we had to train.
Excuse me?
And you just trained that out on
Yes.
handling that.
What was your question?
I think the training data may be also acquired from the web page, because some web pages have keyword indexing for the home pages.
I cannot hear you. Can you please speak louder?
I mean, maybe the training data can be, because if you have too many annotated training data, it's too expensive. But it's also possible to get this. Is it possible to get this online, or for example, Yahoo or other web pages have some keywords? I know some work on the automatic summarization of the web pages. Those works actually extract the keywords from the web pages.
It is not very hard to get. The question was where to get the data, and that it could be easier to get it on the web. And I agree. It is not a problem to get a manually indexed document to train the algorithm with. It is hard to get multiply indexed documents that are indexed by many people. I couldn't find any of those on the internet. But what I was thinking is using, for example, Delicious. They index web pages with phrases that are controlled phrases, and there are many other examples on the internet. I have here a few examples that of phrases that Kea++ actually assigned to the document on the global obesity, for example. Here are the phrases that were assigned by at least 2 indexers, and here Kea++ phrases. It does assign the most important term, overweight, and food consumption was selected by 3 indexers. 3 phrases did not match exactly indexer choices, but are quite similar. There are a few areas that were not matched by that were not extracted by Kea++, and one of the terms did not exist in indexers phrases, but still kind of related to the nutrition area. And here's the same diagram again with phrases that Kea++ selected, and you can see that they're related through agravoc links or the same that the indexer have assigned. Here is another example to introduce you one of the problems with Kea++. Apart from a few things that went wrong while mapping, and it is a particularly bad example, the problem here is that Kea++ failed to match some important areas in the document that indexers were able to identify. Because when phrases are selected into the final key phrase set, we do not check what topic areas they actually belong to, and in this case they all belong to the most important topic, but other topics were not covered. And this is what I'm trying to improve at the moment, and Probably you would know from the text summarization that lexical change is quite useful. Didn't you say that you were working on text summarization? It's a technique to identify sequences of related words in a document. Like cow is related to sheep and sheep is related to wool and so far. And these sequences can help us to identify cohesive structure of the text and how the discourse is flowing throughout the text. We can identify lexical change manually or with a thesaurus automatically. And in the natural language processing, lexical chains were identified with WordNet or Roget thesaurus, and they tend to produce quite useful results for problems like text segmentation, question answering, but they haven't been used yet for keyphrase indexing. I want to show you how such a lexical chain is created on this small example first manually. I start with the term natural disasters, and this is the first element in my chain, and after that I'm looking for words that are similar to natural disaster. Hazard is related. Flash flood is a kind of hazard and kind of natural disaster. Washed away is all related. Flood is a kind of hazard, and flash flood is a kind of flood. So this would be the appropriate place for this term, so I include it here. And there flood occurs against swollen rivers, strong currents, and so far. The longer is the chain, the less is the strength of the chain. If we compute, if the only restriction is the relatedness to the previous member, in this case, yes, there are more terms that can be included into the chain, but there is no space. In this case, for example, strong currents is not really related to natural disaster. We want stronger chains. And there is another way of computing the chains is by including them only if they are related to all elements in the chain, so that a kind of lexical net evolves. I've implemented lexical chain, lexical net extractor with the Agrabah thesaurus, and these are the 3 chains that were identified in this text automatically. The first chain was much longer on the first slide. These words could be included into this chain as well, but they do not exist in the Agrabah, and so I think at this stage it would be useful to have more information, some knowledge base or some lexical resources. Once the chains are computed, we need to weight them to identify the most significant ones. Here is one of the measures proposed 97 that takes into account the number of all occurrences of chain members. In this case, for this chain, it's floods occurs 3 times, natural disaster 1, and landslide 1. So this would be 5. And number of distinct occurrences, which is in this case 3. I don't want to say about the quality of this measure, it's just one example. There are other weighting schemes that take into account the nature of semantic relations between the terms, the graph structure, and I thought it is actually possible to learn the best scoring function by analyzing multiple indexer data. For example, if I take, these are the 6 top lexical nets that were identified automatically from the full text of natural disasters in Vietnam. And these are the terms, the index terms that professional indexer have assigned to this document. So the more of professional indexers' terms are covered in the top lexical nets, the better is our scoring function. In this case, quite a few were mapped with the scoring function from the previous slide. They are marked with bold font. Some terms could not be identified, for example, emergency relief. However, this is another advantage of lexical nets that we can use for this problem. Even if a term does not occur in the document, but according to our controlled vocabulary or our lexical knowledge base, it is related to all members of a chain, we could include it into the number of our candidates, which would be helpful to increase the term coverage of the document. I found here a few pictures of useful useful chains in our life. This is a toilet chain, and lexical chains are particularly practical and useful, as I have shown you, and I'm planning to include them in K++ for different purposes, like identification of better candidates, calculating the features, and most important, measuring the topic coverage into the final in the final index term set. I have a few decisions to make. Should I rather use lexical chains or lexical nets, and what is the scoring function and so far? And I think multiple indexer data could help to find the answer to these questions. This is my final slide. I've been talking about manual indexing, and I hope I could show you that consistency, although important, very difficult to achieve even for professional indexers. For an algorithm, it's actually very easy to be consistent, because for each document in the document collection, the same strategy is used. The problem is the quality. So an algorithm can be consistently bad. But K++ consistency so far is kind of satisfying and not perfect yet. Another problem with manual indexing is that humans' decisions are subjective. If we would ask professional indexer why did they actually select these particular phrases, it would be hard for them to explain. An algorithm can always track back why the phrases were selected. And in machine learning, it kind of learns the subjective scheme from several humans. In my PhD, I just started, it's my first year, and I'm trying to improve K++ performance by using new techniques such as lexical chains, and I'm very interested to see how it performs in other domains and languages. And hopefully there will be a K++ at the end. And the main question that buggers me is whether we could create an automatic system that could perform better than humans, be more consistent, and produce higher quality phrases. Thank you very much.